Okay, 2:30, our next speaker is Carsten Hecht, and he's going to tell us about hardness of approximation for ground state problems.
Okay. Hey everybody, my name is Carsten, and today I'm going to talk about hardness of approximation for ground state problems. And this is joint work with Sevag Gharibian, who is also in the audience and also from Paderborn. Okay, then let's get started. The topic of today is roughly two themes. The first, local Hamiltonians. And usually when we are interested in local Hamiltonians, we're interested in the ground state energy. But we want to shift the focus a bit to think about properties of the ground state. On the second, we are going to think about hardness of approximation. Many problems we are interested in are hard even for quantum computers, and we are interested in if these are possible to solve at least approximately. Right? Now, if you look at these two topics, local Hamiltonians, hardness of approximation, you might think, okay, this sounds a bit like PCP, but our point is to try to combine these topics without quantum PCP, because that has turned out to be pretty hard, and we want to find different ways to show hardness of approximation results. Okay, then we can get started with the main problem we'll be looking at, namely ground state connectivity. In the problem ground state connectivity, or GSCon, we are given a Hamiltonian and two ground states, usually specified by quantum circuits, and we asked whether there's a path of two local unitaries mapping my one ground state to the other, such that every intermediate state in this path is still a ground state, right? So you have the starting state, you apply two local gates, and every state that pops out of that is supposed to still be a ground state. And in the yes case, we will know that there's a short path connecting our ground states, and short means at most m gates. In the no case, every such path will have length at least m prime. Okay. Now, why would such a problem be interesting? From a physical perspective, it asks whether H has a so-called energy barrier. One could imagine, for example, a code Hamiltonian to code words. You could ask whether there exists a sequence of undetectable errors going from one code word to the other. Me, myself, I'm a computer scientist, and for me this is a quantum generalization of classical reconfiguration problems for MaxSet. And this is a natural problem that's QCMA complete, even for commuting Hamiltonians. Okay. The next problem we'll shortly be looking at is called ground state entanglement. We have somewhat of a similar setting. We are given a Hamiltonian, two thresholds, eta 1, eta 2, and a cut partitioning these into two sets. We ask whether there exists a ground state with entanglement entropy eta 1 across the cut we are given, or if every ground state has entropy bigger than eta 2. Now, this problem is very well physically motivated because entanglement structure is a central problem in quantum information. Also, you can listen to the next talk, which is also, I think, about ground state entanglement. Okay. Lastly, I want to stress that this is a different setting compared to the LWE hardness results some of you might know. So recently there were results where you get a distribution of Hamiltonians, and they show LWE hardness of checking the entanglement of the ground space. But for us, we are giving a fixed Hamiltonian, and we are concerned with QCMA hardness, so it's just a very different setting. Good. So now that I've introduced the problems, I can talk about our results. And the main result is that we show that ground state connectivity is QCMA hard and complete, even if we know that there's a factor between m and m prime of n to the 1 minus epsilon, where n is the encoding size, and m prime and m were the lengths of the paths connecting the ground states. We can compare this also to a result from Gharibian and Cliche from 2 years ago at QIP, where they showed QCMA hardness for VQAs with the same ratio. We also get the same result for the ground state entanglement problem, where the gap is just an entanglement, but we get the same gap. The only difference is that the problem is QCMA hard this time, so it might be much harder than QCMA. Lastly, I won't touch on this too much in this talk. We also get the same result for Boolean reconfiguration. This is just the classical version of GSCon. But this is also interesting, especially because lately there have been a few p-space hardness results for classical Boolean reconfiguration problems, but those were in the number of satisfied constraints, right? While we are looking at the path length of the paths. Okay. So then let's see how we are trying to prove these things. First up is the ground-state connectivity hardness of approximation proof. And we are going to look at the following problem. It's called QMSA, and it basically asks, given a circuit V, does there exist a proof of small Hamming rate that is accepted, or is every accepting proof of high Hamming rate? And the Hamming rates are called G and G prime. And this problem might seem a bit artificial at first, but the reason why this is interesting for us is, for this problem we already know that is QCMA hard. For this gap, G prime divided by G is theta of n to the 1 minus epsilon. And this is exactly the gap we want to have for our problems, right? So what we want to do is the gap preserving reduction from this problem to our. What this means is we are given a quantum circuit, and we want to construct a GS-Con instance. So namely a Hamiltonian and a starting and final state, such that in the one case, if we have a low Hamming rate proof that is accepted by the circuit, then we want there to be a short path connecting our ground states. In the no case, only high Hamming rate proofs are accepted, and then we want there to be no short path between the start and final state. And in our case, the start and final state will look pretty simple. On the one hand, we have the all zero state on some large register R and 3 zeros on some switch register S. And the final state looks pretty much the same, just that the switch register is 3 ones. And first up, it is not possible to immediately go from the start to the final state, because we remember in our definition of GS-Con, you're allowed to use 2 local gates. So in one step, you could at most flip 2 of the zeros on our register S, and this would not be enough to flip all 3 at once. Okay. So what's the high-level idea? We are given this QMSA verifier, and we want to map it to a local Hamiltonian whose ground state enforces certain logical actions. So we have to do certain things in order to go from the starting to the final state. We are going to start with the all zero state. And what we'll do next is, first, we need to prepare an accepting proof and the corresponding history state. So the history state is just a state that encodes the whole computation of V, and it's the lower energy state of a certain Hamiltonian if the proof was accepting. After preparing this history, okay, and this can be done in polynomial steps. And this would give us on the register R the history state times 3 zeros in the switch register. Now we can switch on the register S. That means we first flip 2 of the zeros to 1s. Since we prepared a correct history state with an accepting proof, this is a valid state. We can flip the last qubit to 1. This gives us the history state times 3 1s. And now we can just uncompute everything we did on the register R and get the desired final state. Okay. And the goal is we want to make this harder based on the Hamming rate of the proof, right? Because of the flavor of the reduction we are doing. Okay, let's look at this picture. We have in the bottom left, right, our starting state. We have a long path along which we prepare the proof and the history state. At the top, we have the 2 steps where we flip the switch register, and then a wide, longer path where we uncompute everything. And I'm colorblind, but presumably red is the proof preparation. This is really the part we are going to focus on in stock. Now, how are we going to do this? The main idea is to add amplification qubits that will have to be flipped for every proof qubit we want to prepare. That means if we have a high Hamming rate proof, we will have to flip all amplification qubits for each one in that. And because of that, every path will have a large number of steps. Okay. For our construction, preparing one proof qubit will consist of 4 steps. So first, you will be allowed to flip the desired proof qubit, but you will only be allowed to do this at exactly 1 time step. There will be one moment where you can flip the proof qubit. Then you'll be allowed to also flip all the amplification qubits to match it. Afterwards, you can undo the flips on the amplification register. And finally, there will be a check that you have all zeros in the amplification register. Now, how can we enforce this? We use a certain clock construction. You can see here. We have 2 registers K and L. And you see from the time steps on the register K, we always just flip 1 0 to 1. But the right register L is 4 cyclic. And this clock has 3 key features for us. First, if you use the 2 local gate, you can go from one time step only to adjacent time steps, right? You can't skip any. The second thing is, you notice is the second clock is 4 cyclic. And this is because of the 4 steps in our qubit preparation. This will allow us to reuse certain constraints for every proof qubit. In a sense, this is also where the amplification happens in our proof. The third, probably most mysterious feature is if I have 2 time steps, Ti and Ti plus 1, they differ on exactly 2 qubits, and those 2 qubits are the same in Ti and Ti minus 1. So what I mean, if you look, for example, here at the second and third time steps, on the second qubit in register L, we have a 0 and a 1. That means we have a 0 and a 0 and time steps T2 and T1. The reason this will come up later is, for example, if you have a superposition of time steps in T1 and T2, and you want to get rate from the second time step to the third. Since the second and first time step are the same on these registers, it will map my time step T1 into a legal clock state. So this will be a no-go. Good. So now how will this work in practice? Next to the new clock we defined, we will have 3 copies of the proof. The reason we have 3 copies is only a technicality, similar to the switch register, that we can not flip the proof qubit with just 1 2-local gate. And we will have a large amplification register of size n, where n was roughly the size of the input. So let's see how one would prepare a proof qubit. In the starting state, we have all zeros, and this is the unique time step where you are allowed to prepare proof qubit number 1. So this is what we're doing. We're flipping all the 3 zeros to ones in the 3 copies of our proof. Now we flip all the amplification qubits to match it. Next up, we can advance the clock. This makes a check if the amplification qubits match our proof qubit. So this is the case. We can advance the clock farther. Now we are allowed to unflip all the amplification qubits. And lastly, we can advance the clock for one last time. And now there's a check if the amplification qubits are all 0. And we can see that on the register L, we went through all 4 time steps. OK. So remember, right, we had this long path to go from the starting to the final state. And right now, we are only looking at the preparing accepting proof stage. But how do we go about showing soundness in total? We will use the so-called traversal lemma to show that from every path from the start to the final state, at some point, we'll have large overlap with a state orthogonal to the 3 zeros or 3 ones in our switch register. This will mean that at some point, the check will be activated to see if we prepared a history state with an accepting proof on the register R. Now, preparing such an accepting proof will take n times g prime any 2 local unitaries. Remember, n was the number of amplification qubits, g prime was the Hamming rate of the accepting proof. And for every 1, right, we need to flip all the amplification qubits, and this is where we get this n times g prime. Now, we saw this is the case, for example, in our example with the first proof qubit, that this happens if the prover can only use X gates. But in our case, you can use arbitrary 2 local unitaries, right? And we had constraints in certain time steps, you can only use certain things. But in general, if you, for example, create superposition over all the time steps, it makes it much harder to argue about, okay, what can you do with 2 qubit unitaries? What kind of states can you prepare? And this is where the third key feature of our clocks comes in. And we can show that on our new clock, all the rate is at pretty much all times on 2 consecutive time steps. And this will help us to allow to recover the gates, the arguments for the X gate case, right? Because all the rate is on 2 consecutive time steps, so these move through the clock register, and we can say, okay, we are pretty much at this time step. Then you have kind of to do this, but in the paper, this is also the most technical part is to show that a prover can actually do not much better than using X gates to flip all the amplification qubits with 2 local unitaries. Okay. Okay, now how we're finishing the proof. We saw that in order to go from the starting to final state, in the first case, in the S case, we will need to do roughly g times n many flips, because there g is the Hamming rate of the exacting proof. In our case, we need g prime times n many gates. And when we look at the approximation ratio, we get g prime divided by g, which is exactly the theta of n to the 1 minus epsilon. But here n is still the size of the QMSA instance. And an important step here still is to show that this is also theta of n to the 1 minus epsilon for n being the size of the GSCon instance. But since we were careful with our constraints, right, we had the cyclic clock with constraints we could reuse for every proof qubit, we can show that the size of our GSCon instance is linear in the circuit size for the QMSA circuit, by which the theorem follows. Okay. Now we can do short and sweet for the ground-state entanglement problem. Here we use pretty much the same strategy to get the result. We do the reduction from QMSA. We use the high, low Hamming rate proofs to create the right number of bell pairs. We do the circuit to Hamiltonian construction, this time with weighted terms. The weighted terms we can use the projection lemma to argue, okay, every low energy state has to roughly look like a history state. For the history state, we do know the entanglement across the chosen cut. And then we can use Fun's inequality to argue, okay, every low energy state is roughly a history state. For that one, we know the entanglement, and so we know the entanglement for every low energy state. Okay. Then let's come to an end. So what did we show in our work? We showed that the ground state conductivity problem is strongly hard to approximate with respect to the path length. We have the same results for the classical analog Boolean reconfiguration and for the ground state entanglement problem. And the main kicker was that the results were obtained without the use of the PCP theorem. Open questions are if we can use the same trick to show hardness approximation for more problems. Another interesting question is, right, we had hardness approximation in the path length compared, for example, the number of satisfying constraints in the p-space hardness results I was talking about earlier. And lastly, there's a few multiple ways to state this GSE problem, like how hard is this problem in general for which statement. Okay, that's already it. Thanks very much for listening.
Great, we have plenty of time for questions.
So your result is for Hamiltonians with local terms that on 5 qubits. Do you think that it holds for lower locality?
The clock constraints we have and things like that, right? We usually have constraints that are on, like, for example, the 3 proof copies, right, and something else. So our constraints are pretty large, but we can, I think, make it only work for 5 local. So we did check for the constraints, right, how local it can go. And I think we said it's for 5 local. And I think that's already with the 2 local Hamiltonian construction. So we do it constraints with more locality.
Okay, thank you.
Okay, maybe I get a quick question. Can you comment on this last bullet point on the slide? Like,
yeah, I mean, there's different ways you can phrase it. For example, I mean, we should use some hardness for our version. You can, for example, for us, it was not necessary to pinpoint like the energy of the Hamiltonian, because in our reduction, in the yes no case, the energy is both pretty much 0. But that could be like part of the question, or you could ask, does there exist ground state with low entanglement entropy? Does there exist a ground state with high entanglement entropy? So there's just different ways to phrase it, and it could be interesting for multiple stuff, for multiple things. Yeah.
okay, if there are no other questions, then let's thank Carsten again.